Hello everyone, my name is Jianyu Wang, and I'm going to talk about this work, Adaptive Communication Strategy in Local Update SGD. This is a joint work with my advisor, Professor Gary Josh. We are from Carnegie Mellon University Parallel Data Lab. To start with, please let me first do a very brief overview of this work. As we know, stochastic gradient descent is a backbone of modern machine learning, and especially the backbone of deep learning. And it can efficiently find the minimum of any objective function. And when we run SGD on a single machine, what we care about is the training progress per iterations. And this is so-called error convergence. In the machine learning community, there has been a lot of work to accelerate the error convergence. For example, SGD with momentum, the adaptive method, and variance reduction method. However, nowadays, because we have larger and larger data set and deeper neural networks, so running SGD on a single machine can be prohibitively slow. So there is a critical need to parallelize SGD algorithm onto multiple machines. When it comes to the multiple machines, when it comes to the distributed setting, we not only need to care about the error convergence, but also need to care about the system's throughput. That is the iteration per workload time. And in the practice, what we really care about is actually the training progress per workload time. It's a multiplication of these two factors. And because deep neural network has so many model parameters, and in DNA training, the system's throughput can be the bottleneck. So recently, there are many distributed SGD variants are proposed to increase the system's throughput. But on the other hand, they also hurt the model quality. They will slow down the error convergence. So we can see there is a trade-off between the system's throughput and the error convergence. We call this the error runtime trade-off. And in this work, we try to propose some method to balance this error runtime trade-off, and we try to maximize the training progress per workload time. And this is a very brief overview of this work. So now I'm going to introduce a basic background of distributed SGD algorithm. Let's first have a look at the execution pipeline of synchronous SGD. Suppose we have total M worker nodes here, and the first step of synchronous SGD is local computation. Each of these worker nodes will locally compute their stochastic gradient with respect to the current model parameters. And these blue arrows denotes the computation time. And then after the gradient computation, we need to average the stochastic gradients across all the worker nodes. So there is a communication step. The red block denotes the communication time. And this communication can be either completed by a parameter solver or reduced operation. And it will cost some time. And the algorithm will repeat the gradient computation and the communication step again and again until convergence. And we can see from this execution pipeline, actually the communication time is nearly occupies half of the time. And if we compare it to the ideal case, where there is no communication at all, we can see in the ideal case, it finished 10 iterations in the given time. But in the practice, because we have the communication overhead, it only finished 6 iterations. So the communication overhead significantly affects the speed up offered by this program. And what makes things worse is that actually in the deep neural network training, because deep neural network has so many parameters, and the communication time can be even longer or multiple times than the computation time. And in some cases, we cannot expect any speed up provided by this parallel program. So to address this issue, previous researchers proposed a very promising solution that is periodic averaging SGD. It allows different worker nodes to perform tau local steps before the communication. And we refer tau local steps here as a communication period. And this algorithm can be also considered as a special case of federated averaging algorithm. And we can have a look at the execution pipeline again. Instead of having the communication step after every gradient computation step, in periodic averaging SGD, it will allow some local steps. The communication happens after every tau iterations. And in this tau example, tau equals to 3. We can see previously the 6 iterations and there, and now 7th iterations and here. It greatly improves the system's throughput. And basically, we will have 2 benefits of using periodic averaging strategy. The number one is communication amount will be directly reduced by tau times. And the second is the variations in computation delay are also evened out. To have a clear view of what is the benefit of periodic averaging, let's have a look at this plot. It shows the runtime distribution distribution of different algorithms. The red histogram corresponds to periodic averaging tau equals to 10, and the blue histogram denotes corresponds to the synchronous SGD. And basically, we run many iterations and record the runtime per iteration. We can see actually the red histogram is has a much lighter tail than the blue histogram, and the mean runtime nearly achieve a 2 times speed up than the synchronous one. So this is a benefit of using periodic averaging. But on the other hand, we also note a limitation of this method. That is, it may lead to a worse convergence. Let's have a look at this model parameter space. The yellow circle denotes the local model at worker 1, and the green circle denotes the local model at worker 2. If we use a large communication pair, that means these two local models will be far from each other. And it's possible that they fall into different local basins. And in that case, we cannot guarantee the average model is better than two individual models. And we also have some theoretical support for this statement. Theoretical results tell us that the optimization error at convergence will be bounded by these two terms. The blue block is identical to the error of synchronous SGD, and the red block is an additional noise because of performing local updates. It's linear to the communication period tau. So eta is the learning rate, and L is a Lipschitz constant. Sigma square is a gradient variance bound. So it tells us using periodic averaging has a higher optimization error. So to sum up, using a large communication period will help us to increase the system's throughput, but it will also give a worse error convergence. So combine these two together, what we really care about is the training progress per workout time. There is a trade-off. To have a closer look, that means if we're using a large communication pair, it will decay very fast at the beginning, but converge to a high error floor at the end. And on the other hand, if we use a small communication period, it will decay very slowly at the beginning, but converge to a better model at the end. The key observation here is that actually the best communication period varies over time. Before the intersection point of these two lines, a larger communication period is more preferable. But after the intersection point, a small communication period is much better. So based on this observation, our goal in this work is to design some adaptive communication strategy, which starts with a large communication period and gradually switch to a smaller one. And our approach is to use theoretical error runtime analysis to decide how to switch between different curves. Okay. Now I'm going to give an overview of our proposed scheme. And for brevity, we will first consider the fixed learning rate case. The first step of our scheme is to divide the training progress into multiple intervals. And T0 here is a time interval length. Maybe it can be several minutes, maybe 10 minutes or 20 minutes. And then within each time interval, the communication period is fixed. And then the second step is to estimate the best communication period for each time interval. So for the 0th time interval, we have tau 0, and the first time interval, we have tau 1, and so on and so forth. So now the question is, how can we estimate the best communication period in each time interval? And our approach is to combine the runtime and the convergence analysis. From the theoretical result, we can know the optimization error can be bounded by these three terms, and our approach is very simple. We just simply replace the iteration index by the workout time. So we get the optimization error after time t. It will be bounded by these three terms. And if we have a closer look, the first term will be decreased along with the increase of communication period tau. But the last term will increase with along with the increase of communication period. So there is a trade-off. A heuristic choice of the best communication period is to just take a derivative of this upper bound and set it to 0. And we get this adaptive communication strategy. It shows the best communication period after workout time capital T. But actually, it's very hard to use this adaptive strategy because there are so many unknown constants. For example, the Lipschitz constant and the sigma square. So in order to address this issue, we propose another strategy. Recall that actually we divide the training progress into different time intervals. So for each time interval, we can using this formula. For the first time interval, we can derive this expression, and for the else time interval, we can get this expression. So the only the only difference between these two expressions is the training loss. All other constants are equal. So what we do is very simple, just compute the ratio between these two communication periods. So we can see in order to determine the value of else communication period, we just need to know the training loss, and which is very easy to obtain in the training progress. And we also need to know the initial communication period tau 0. And to estimate tau 0, we just do a manually grid search at the very beginning of training. And to have an overview of our proposed scheme, let's have a look at this illustration. In the first time interval, we will estimate the tau 0 via grid search, and we train it for t0 time. And at the t0 time, we use the training loss at the t0 and the initial communication period to determine the tau 1, the best communication period at the first time interval. And then we use the training loss at time 2t0 and the initial communication period to determine tau 2, the best communication period at the second time interval, and so on and so forth. We get the training process of adaptive communication strategy. And the updated rule of adaptive communication strategy can be formulated as this. And we can see the communication period will proportional to the square root of training loss. And an interesting observation here is that actually the communication period will gradually decrease along with the training loss. And this matches well with our initial intuition that using a large communication period is much more preferable at the beginning, but a small communication period is much better in the later stage of training. And another important and interesting observation is that actually we can make a connection to the learning rate decay. We have the same trade-off and the same motivation. Recall that actually when we run SGD on one single machine, what we care about is the training loss versus the iterations. And when we use a large learning rate, that means we will decay very fast at the beginning, but converge to a higher error floor at the end. But if we use a small learning rate, it will decay very slow at the beginning and converge to a better model. So based on this trade-off, we design a lot of adaptive learning rate strategies. For example, the stage-wise decay, the exponential decay, ADA-grad ADAM, and a lot of works on this direction. But in this work, because we are focused on the distributed setting, what we are care about is the training loss versus workload time. And we observe the same trade-off as the learning rate decay case. And the difference is that what we optimize here is the training loss versus workload time. And the learning rate case is this optimize is the training loss versus the iterations. And we feel that in this direction, there are a lot of work can be done about adaptive communication strategy in the future. And the key insight here is actually decaying communication period is in spirit similar to decaying learning rate. And also, these two schedules can also be combined together. We can, in our adaptive communications strategy, we can also incorporate with adaptive learning rate. And to do so, we just need to rescale the communication period when the learning rate is decayed. And because time is a little bit limited, I cannot tell too much detail here. So now we can have a look at the experimental results. We evaluate our adaptive communication strategy on CFR10 and the CFR100 data set with 8 worker machines. Each machine has one Titan X GPU, and we evaluate the algorithm on 2 tasks. The first task is communication intense task. We can observe from this plot as we increase the communication period, the yellow line and the red line decays very fast at the beginning, but it will converge to a very high error floor. And on the right hand side it is a computation intense task, and we can see although we use a large communication period, but it will give a worse convergence. So even at the beginning, it cannot give us any benefit in the training loss versus workload time plot. So we can have a look at our adaptive communication strategy. The black line we can achieve a win-win in this training loss versus workload time plot. We can decay very fast at the beginning and achieve the same training loss as the synchronous SGD algorithm. And it's also worth to noting that our strategy is we won't monotonically decay the communication period. The communication period will have an increase when we decay the learning rate. We can see from the bottom, we can see how the communication period changes. And this is a comparison of the test accuracy. We can see our adaptive communication strategy achieve nearly the same test accuracy as synchronous SGD, and using a large communication period will hurt the test accuracy. So now I'm going to conclude this talk. First, in this work, we propose an adaptive communication strategy that can work very well in practice. We achieve up to 3 times speed up over synchronous SGD algorithm. And this strategy is conceptually similar to adaptive learning rate. And in adaptive learning rate, we have already a lot of existing works. And when it comes to adaptive communication strategy, we feel a lot of future works can be done. And the similar trade-off, the trade between the error convergence and the runtime can also exist in other distributed SGD variants. For example, in decentralized parallel SGD, instead of controlling the communication period, we can control the connectivity of the worker network. And in synchronous SGD, we can control the number of nodes to wait at each iteration, and a lot of future works can be done in these directions. Okay, that's all. Thanks for your attention. Any questions?
Yeah, this is Minchik from IBM. So I have I want to make sure that I understand everything correctly. So here you're suggesting that in the beginning of a training, we can use, let's say, the large running rate, and then we can have a big, let's say, the intervals between communication.
Yeah.
Is that right? And then in the later stage, we need to do it the other way.
Yes.
But this is a kind of a counterintuitive. For example, if you take a look at Facebook's 2017 paper, they started with a very tiny running rate as like a warm-up phase. And then they stated that that's a crucial technique to make sure that less than 50 can converge in an hour. And then second intuition is that in the beginning, you don't know where you are sitting on in terms of solution space. So you need to be very careful. But in the later stage, already this is kind of a done deal. You are already like deep inside the valley. So no matter what kind of communication you do, perhaps it doesn't matter. So my intuition is that in the beginning, we need to be very careful in navigating this solution valley. That means that we need to have a very frequent communication. But in the later stage, already you are at the bottom of the solution space. So no matter what you do, it doesn't matter much. So that means that perhaps it is okay to have a very large communication interval. But your explanation is very counterintuitive to my understanding. So do you have any comment on my intuition?
Yes.
If you think I'm wrong, I'd like to get corrected as well.
Okay, thank you for your question. Yes, I would like to share with you my intuition about this problem. Actually, my insight about this is actually in the beginning of training, because we are using stochastic gradient design. So at the beginning of training, maybe the gradient is very accurate and the variance of gradient is very small. So at the beginning, a large derivation between local models doesn't matter. But at the end of training, the variance of gradient will dominate, and the gradient, and we cannot make progress because of the noise in the gradients. And so in that case, we must use a small communication period to reduce the noise in the stochastic gradient so that we can achieve a better model quality. Yeah. Okay, we can discuss offline about this. Yeah. Okay.
My name is Ashraf. I have a question. So you said you are getting this speed up in comparison with synchronous SGD. My question is, how do you compare it with like a simple SGD? Do you have any comparison with that? Because like in the beginning you said like synchronous SGD might be even slower than a simple SGD on a single machine because of the old communication costs and everything. But you don't have any comparison with like a simple SGD like over here to see like how is the result over here?
Sorry, you mean the comparison to other communication efficient SGD algorithms?
No, I'm saying like over here you're saying you're getting this speed up in comparison with synchronous SGD. But in the beginning you said synchronous SGD might be even slower than like having a simple like SGD in a single machine because of all the communication costs. But I'm saying, do you have any comparison with your method and like a simple SGD to see if you're getting any speed up or like over there?
I see. Synchronous SGD is slower than the serial version in the worst case. Even it's only the case when the network bandwidth is very, very slow. And actually, in practice, synchronous SGD it will be faster than the serial version. Yeah.
Okay, we could do one more quick question while Jian sets up.
Okay.
Thank you. Jung-wook from IBM. I think it's very interesting result. I'm just wondering if the result can be some dependent on some hyperparameter, especially mini batch size.
I don't think so. It's you can assume it's incremental algorithm of synchronous SGD. You can keep the batch size as the same as synchronous SGD, and based on that we can apply our algorithm.
But can you increase the mini batch size and scale the learning rate in the same way that people do for distributed deep learning?
Yeah, I feel so. We can do that, and based on that we can implement our algorithm upon that. Yeah.
Okay, thank you.
Okay, great. Let's thank the speaker.